Stand at the edge of this place and your nerves start humming, whether you want them to or not. This is Dearborn, Michigan, the beating heart of American industry, where a brand new Ford F-150 rolls off the line every 53 seconds. For 49 years straight, almost half a century, the F-Series has been the best-selling truck in the country, and nobody else even comes close. Close to 800,000 of them sell in the United States every single year. If one bolt stops turning here for 5 minutes, the company bleeds hundreds of thousands of dollars, and the whole truck market feels the shudder. This is a giant machine running at extreme stakes, where a single mistake costs millions. I came here to watch with my own eyes how roughly 9,000 parts turn into a legend in about 20 hours, with around 1,000 pairs of hands on every truck. Trust me, it makes your head spin. The colossal gamble at the core of all this started a little over 10 years ago. In 2015, the people running Ford made a call that plenty of folks flat out called business suicide. They ripped steel out of the truck's body and switched the whole thing to military-grade aluminum. Why the panic? Aluminum is lighter than steel by about 700 pounds, roughly 320 kilograms, which lets the truck haul more and burn less fuel. But working with it is a nightmare. You can't just weld it the easy way you weld steel, because it melts and cracks under an ordinary welder. Ford bet everything, billions of dollars, shut factories down for weeks. If that experiment had failed, the company could have gone under, because this one truck feeds the entire corporation. And it all begins in the stamping shop, where the noise hits you like a wall. You feel it in your chest before you hear it. Giant presses in here weigh thousands of tons, some pushing past 3,000 tons of force, around 2,700 metric tons. They slam down on huge coils of aluminum so hard the ground moves under your boots. One strike, and a flat sheet becomes a finished door or a hood. The tricky part is that aluminum has a memory. Press a hair too soft or a hair too hard, and the panel either springs back or tears, and all that expensive metal goes straight to scrap. The tolerances here are measured in thousandths of an inch, a few hundredths of a millimeter, and laser scanners watch every curve. Next, we step into the body shop, and this is where the F-150 really breaks the rules. Because aluminum hates being welded the old way, they barely use classic welding at all. The body is held together by more than 2,700 self-piercing rivets and over 300 feet of structural adhesive, about 100 meters of glue. The robots move so fast your eye can't keep up. They fire rivet after rivet, thousands per truck, and that glue is stronger than the metal it bonds. Once it cures inside special ovens, the whole structure goes nearly solid, one single piece. The roof is the only spot they still weld, and they do it with a laser for a clean, seamless seam. It all demands perfect climate control. If the humidity shifts even a few percent, the adhesive won't grab right, and the cab could come apart in a safety test. No other mass-market brand on the planet does anything like this at this scale. Once the body is together, it heads into the paint zone, a fully sealed, sterile area where people only go in wearing what look like spacesuits, so not one speck of dust ruins the finish. First, the truck gets fully dunked into massive tanks of chemical bath, where an electric current lays down a rust-proof coat that reaches every hidden corner. Then, automatic sprayers put down layer after layer of paint and clear coat. These paint lines run for miles, and the truck moves without stopping until it gleams like a fresh minted dollar. Any flaw here means stripping it back to bare metal, and that is a brutal loss of time, which around here is worth more than gold. Remember, we are always counting down those 53 seconds. Meanwhile, on a separate line, they build what Americans call the backbone of this machine, the heavy steel frame. Unlike the body, the frame stays steel because it has to take a savage beating, tow trailers weighing thousands of pounds, several metric tons, and ride hard over rough ground. Onto this frame go the suspension, the big axles, the brakes, and the fuel tank. The engine and transmission get dropped in here too, but I'll spare you the deep dive on the powertrain. That is a whole story of its own. A crane lowers the heavy assembly within a fraction of an inch, and workers torque down the massive bolts with pneumatic tools. Every bit of force is logged by a computer. If a bolt is under-tightened by even a quarter turn, The system locks the line, and everything stops until somebody fixes it. And now we reach the moment that matters most. They call it the marriage. This is when the finished aluminum body comes down from above and settles onto the steel frame already loaded with the powertrain. It looks incredible and a little terrifying at the same time. Two enormous halves of a truck, built at completely opposite ends of the plant, have to meet at one point and line up to a single bolt hole. People and machines work it together. The body glides down, workers guide it in, and in a couple of minutes, the two halves become one. This is make or break, because if anything goes crooked here, fixing it on a moving line is almost impossible. Once the base is whole, the truck rolls into final assembly, where the real controlled chaos kicks off, in the best sense of the word. Thousands of small parts come flying in: headlights, the grille, bumpers, the windshield, the interior trim. The cabin gets built on its own line, where workers fit the huge dashboard, the leather-wrapped seats, and all the electronics. And every piece shows up at the exact second the right truck pulls up. So if a fully loaded top trim pickup with a red interior is coming down the line, the system feeds it the red seats, not the black ones. A mistake is basically impossible because every truck carries its own unique barcode, scanned by sensors at every step. The last stage is filling all the fluids, the fuel, and firing up the engine for the first time. When the truck starts on its own and drives itself off the line, you feel this strange wave of relief. But it is way too early to relax, because a brutal quality control zone is waiting. Every pickup gets run onto a special rig where the wheels spin at high speed, and they check the brakes, the transmission, every safety sensor. After that, the truck goes through what they call the water tunnel, where thousands of gallons of water blast it from every direction under serious pressure. It is a leak test. If even one drop sneaks into the cabin, the truck gets pulled and torn back down. Watching this endless river of trucks roll out, you understand why the Ford F-150 has held the crown for almost half a century, and why almost nobody on Earth can copy it. Building an exotic supercar in batches of a few dozen a year is hard, but building a system that spits out a reliable, high-tech, massive pickup every 53 seconds, hundreds of thousands of them, year after year, that is a real test of the human mind. Every move here is locked down and calculated, every risk shaved to the minimum, and the level of engineering just forces you to respect the people who dreamed all of this up. This was an incredible trip into the making of a legend. And now I know exactly how American automotive history gets forged. If this blew your mind even a little, subscribe to Made on Earth, because we take you inside the machines and factories that quietly run our world. Somewhere in Buffalo, New York, sits a building so big it has its own weather. 3.1 million square feet of steel and concrete, the single largest engine plant on the planet.
General Motors set to make a major investment at its propulsion plant in the town of Tonawanda. $888 million will be used to install new machinery, equipment, and tools, along with other renovations there.
And inside, on a good day, a finished V8 engine rolls off the line every 10 seconds. 8,500 of them in a single day. Since this place first opened, it has built more than 63 million engines. Stack that up, and you've powered most of a century of American muscle. But here's the part nobody tells you. To turn a puddle of molten metal into 8 cylinders that fire 24,000 times a minute, this factory has to pull off something that sounds impossible. Stick around, because the way they do it is wilder than anything under your hood. Let's start with the scale, because the numbers are genuinely hard to believe. This one plant builds roughly 35% of every engine the company makes worldwide. 5 assembly lines run at once. At full tilt, that's a complete running V8 every 10 seconds, more than 8,000 a day. Think about that. In the time it takes you to read this sentence, 3 more engines just got finished. Now, a modern V8 isn't one part. It's around 1,000 separate pieces, each machined to a tolerance you can't even see, all coming together in a few hours. And it all begins with metal so hot it glows like the sun. Because before you can build an engine, you have to pour one. It starts with the block. The block is the skeleton of the entire engine, the giant chunk of metal that holds the cylinders, the crankshaft, everything. And most modern V8 blocks are cast from aluminum. In the foundry, Solid aluminum gets dropped into a furnace and heated to around 700 degrees Celsius, that's 1300 Fahrenheit, until it turns into a glowing silver liquid. For comparison, aluminum melts at 660 degrees, so they're pushing it well past the point of no return. Then comes the pour. Workers guide that molten metal into a sand mold shaped exactly like an engine block, hollow channels and all. Inside, cast iron sleeves are often locked in place, the surfaces the pistons will ride against. The metal floods in and cools. A few minutes later, they break the mold apart, and there it is. A raw engine block, born from a bucket of liquid metal. But it's nowhere near ready. Right now, it's accurate to about the width of your finger, and an engine needs to be accurate to the width of a hair. This is where the factory turns into a surgeon. The rough block gets clamped into a CNC machine, a computer-controlled cutting station the size of a small room. Spinning tools come down and shave the metal, drilling the cylinder bores, cutting the bolt holes, flattening the deck where the head will sit. And the precision here is almost absurd. The cylinder surfaces are machined to within a few microns. To put that in perspective, a single human hair is about 70 microns thick. These tolerances are 5 to 10 microns. That's roughly 1/14 of a hair. Cut too much, the engine leaks power. Cut too little, the piston sees. So every block is measured, scanned, and logged before it's allowed to move on. One factory, building thousands a day, and each one held to a standard you'd need a microscope to check. Now for the heart of the whole machine, the crankshaft. This is the long steel bar that turns the up and down punch of the pistons into the spinning motion that drives your wheels. And it takes a beating like nothing else in the car. So they don't just cut it from a block, they forge it. A glowing hot steel billet gets slammed under a massive press, hammered into the rough crankshaft shape under thousands of tons of force. Forging packs the metal's grain tight, making it far stronger than a cast part. Then it goes to the machines, where the bearing journals, the surfaces that spin inside the engine, are ground down to between 5 and 10 microns. After that, it's spun and balanced, because a crankshaft turning thousands of times a minute that's even slightly off will shake an engine to pieces. One unbalanced gram, multiplied by all that speed, becomes a hammer blow. Get it perfect, and it spins smooth for 200,000 miles. With the block machined and the crankshaft ready, assembly begins. And this is where 1,000 parts start fitting together like a puzzle. The crankshaft drops into the bottom of the block. Then come the pistons, 8 of them, connected to the crank by steel rods. Each piston has to slide into its cylinder with a clearance thinner than a sheet of paper, tight enough to seal the explosion, loose enough to move at the speed of a bullet. On top goes the cylinder head, packed with valves, springs, and camshafts that open and close in perfect time, hundreds of times a second. And here's the wild part. On these modern lines, almost nothing is guessed. Every single bolt is tightened by a smart tool that records the exact torque and feeds it into a database. Every block carries a barcode, and the system tracks every step. If a worker skips one, the line refuses to move forward. The engine literally won't let itself be built wrong. Watch the line and it almost looks alive. Robotic arms swing oil pans and timing covers into place. Fuel rails, sensors, and miles of wiring get threaded around the block, because a modern V8 is as much a computer as it is a machine, stuffed with sensors reading temperature, pressure, and the position of the crankshaft hundreds of times a second. Spark plugs go in, the intake manifold caps it off, and piece by piece, that rough chunk of cast aluminum from the foundry has become a complete, intricate, 1,000-part machine. But the factory still doesn't trust it. Not yet. Because a V8 that looks perfect can still hide a flaw you'd never see with your eyes. And the only way to find it is to make the engine come to life. So before this engine ever touches a car, it gets tested. First comes the cold test. The engine is hooked to a machine that spins the crankshaft electrically, turning it over without ever firing a single spark. Sensors listen to everything. Compression in each cylinder, oil pressure, the faintest leak, vibrations far too small for a human to feel. In seconds, the computer knows if anything is even slightly off. Some engines go further, onto a hot test, where they're actually fired up and run, roaring to life on a stand, and pushed under load to make sure they deliver the power they're supposed to. Every reading gets saved against that engine's barcode, forever. If it fails by even a hair, it's pulled. Only the ones that pass, flawless, get sent out the door to drop into a real car. And this is the payoff for all that obsession. A finished V8, like the 6.2-liter monster these plants build, makes nearly 500 horsepower. Supercharge it, and you're past 750. At 6,000 revolutions per minute, those 8 cylinders are firing 24,000 controlled explosions every single minute. That's 400 tiny, contained detonations every second, all perfectly timed by parts machined to a fraction of a hair, balanced to a single gram. Now, compare that to the other end of the spectrum. At Mercedes-AMG, they go the opposite way. One master technician builds an entire V8 by hand, start to finish, in 4 to 5 hours, then signs his name to a badge bolted right onto it. One engine, one human, one signature. Two completely different philosophies, the factory that builds one every 10 seconds, and the craftsman who builds one a day, both chasing the same impossible perfection. So the next time you hear a V8 rumble at a stoplight, remember what it actually took. A puddle of metal heated past 1300 degrees, a block carved to a fraction of a hair, a crankshaft forged under thousands of tons and balanced to a single gram, 1,000 parts, every bolt logged, every engine tested before it ever turned a wheel, pouring out of the largest engine plant on Earth at a rate of 1 every 10 seconds. It's one of the most extreme manufacturing feats humans have ever pulled off, hiding in plain sight under a hood. If this blew your mind even a little, subscribe to Made on Earth, because we take you inside the machines and factories that quietly run our world. And go watch how the Gigapress casts an entire car body in 80 seconds next. Trust me, you're not ready for that one.
Stand beside the world's largest diesel engine. It towers 44 feet tall, higher than a 4-story building, stretches 89 feet long, longer than a semi-truck with trailer. 14 cylinders, each wider than oil drum, fire in sequence, producing 109,000 horsepower. That's the power of 1,600 cars concentrated in one single machine. This engine burns 250 tons of fuel daily, moving 20,000 containers across oceans at 23 knots. How does metal combusting heavy fuel oil generate force pushing 90,000-ton ships through water? Why build engines this enormous when smaller multiples could work? Stay with us. You'll discover the brutal elegance of two-stroke combustion at massive scale, and the shocking secret of why these engines burn fuel refineries consider waste. The cheapest, dirtiest. Our journey begins at Hyundai Heavy Industries in Ulsan, South Korea, the shipyard building these mechanical titans. The engine manufacturing hall spans 30 acres under single roof. Overhead cranes rated at 600 tons glide on rails, positioning cylinder blocks weighing as much as locomotives. Workers look like ants beside components. Watch the cylinder casting. Molten iron pours into sand molds, creating a single cylinder liner, hollow tubes where pistons travel. Each liner stands 12 feet tall, walls 4 inches thick. The iron must cool for 72 hours. Rush it, thermal stresses create microscopic cracks that propagate under operation, causing catastrophic failure. We make engines that run 30 years continuously, explains Chief Engineer. No second chances if casting fails.
The crankshaft arrives on specialized trucks, a single forged steel shaft weighing 300 tons, machined to tolerances measured in thousands of inches across 70-foot length. Installing it requires choreographed precision. Hydraulic jacks lift the shaft while technicians align bearing surfaces. One misalignment of ½ inch causes bearing failure within weeks of operation. Picture the assembly floor. 14 cylinder liners bolt to engine block, itself a 40-foot steel casting, forming engine skeleton. Each connection uses bolts diameter of baseball bats, torqued to specifications requiring pneumatic impact wrenches lasting 5 minutes per bolt. Assembly takes 6 months, 12-hour shifts, teams of 50 engineers and technicians. One finished engine represents 200,000 man-hours, equivalent of one person working full-time for 96 years straight.
The pistons dwarf automobile engines. Each piston assembly, piston, rings, and connecting rod weighs 6 tons. That's heavier than full-sized pickup truck. The piston crown, exposed to combustion, endures temperatures exceeding 1,800 degrees and pressures reaching 2,000 psi. Material science pushes limits here. Watch piston installation. Cranes lower assemblies through cylinder tops. Workers guide them onto connecting rod bearings with millimeter precision. The piston rings, spring steel bands sealing combustion pressure, get installed by hand. Each ring expands under tension, slip during installation, and the ring snaps, injuring workers and destroying components worth $50,000. Veterans develop feel for tension, installing rings quickly yet carefully. 20 years I've installed 3,000 pistons, says one assembler. Still respect every one.
Now grasp two-stroke operation. Elegantly simple, yet counterintuitive. Unlike car engines firing every other rotation, marine diesels fire every rotation. As piston descends, it uncovers ports in cylinder wall. Compressed air rushes in, pushing exhaust out simultaneously. The piston rises, compressing fresh air. Near top, injectors spray heavy fuel oil. Compression heat, not spark plugs, ignites fuel. Explosion drives piston down. The cycle repeats. This two-stroke design eliminates valves entirely. No camshafts, no timing chains. Fewer parts mean greater reliability. But it demands supercharging. Turbocharges forcing air into cylinders at 22 psi. Without pressurization, the engine wouldn't breathe. Turbochargers the size of sedans spin at 20,000 RPM, driven by exhaust gas. They glow red-hot during operation, requiring water cooling systems circulating thousands of gallons hourly.
Fuel injection happens at extreme precision. Each cylinder consumes 16 gallons per combustion cycle, enough to fill your car's tank every few seconds. Injectors spray fuel as fine mist under 6,000 psi pressure. The atomization must be perfect. Droplets too large won't burn completely, wasting fuel. Too fine, combustion becomes explosive rather than controlled, damaging engine. The fuel itself surprises people. These engines burn heavy fuel oil, basically petroleum refinery leftovers after extracting gasoline, diesel, and jet fuel. It's thick as molasses at room temperature, must be heated to 240 degrees before flowing. Contains sulfur, metals, and contaminants that would destroy car engines instantly. But marine diesels tolerate it because economics dictate everything. Heavy fuel costs 40% less than automotive diesel. At 250 tons daily, that price difference means millions saved annually per ship.
Engine control happens from bridge via computer systems monitoring 600 parameters simultaneously. Engineers track cylinder temperatures, bearing pressures, fuel consumption, turbocharger speeds. The engine room, 3 decks tall, deafeningly loud despite ear protection, houses the mechanical orchestra. Walk the engine room during operation. Heat radiates from every surface. Metal creaks and groans as thermal expansion moves components fractions of inches. Across a 70-foot engine, that's feet of total movement. The crankshaft, visible through inspection ports, spins at 102 RPM. Seems slow until you realize this massive shaft accelerates tons of metal from 0 to maximum speed every single rotation. The forces involved bend physics. One chief engineer describes it, "This isn't machinery, it's controlled violence. We're detonating tons of fuel hourly inside metal box, converting explosions into rotation." Maintenance happens at sea on schedules measured in years. Every 8,000 hours, roughly 1 year of operation, crews perform major service. They drain lubricating oil, 60,000 gallons per engine, replacing filters the size of trash cans. Inspect cylinder liners for wear using ultrasonic equipment. Pull pistons for ring replacement. The most dramatic maintenance involves crankshaft inspection.
Engineers use magnetic particle testing, apply magnetic field, spray iron particles, look for cracks where particles accumulate. Finding cracks in 300-ton crankshaft spinning at 100 RPM means potential catastrophic failure. The process takes 4 days of continuous work while ship sits idle, losing $200,000 daily in lost revenue. But catching cracks before failure saves the engine worth $15 million. No shortcuts exist. We maintain like lives depend on it, states Chief Engineer, because they do.
Rudolf Diesel invented compression ignition engines in 1897, demonstrating fuel efficiency double that of gasoline engines. His original design ran on peanut oil. Diesel envisioned farmers powering equipment from crop byproducts. The petroleum industry hijacked his invention, optimizing for their cheapest product, heavy fuel oil. Marine applications began in 1920s. By 50s, diesel surpassed steam turbines. The two-stroke design, perfected by Sulzer and Wärtsilä through 70s and 80s, became dominant. Today's largest, the Wärtsilä-Sulzer RTA96C, produces power exceeding small city power plant. Just 14 cylinders generating 109,000 horsepower. 23,000 containers moved by single engine. 98% of ocean cargo moves via diesel-powered ships. These engines literally keep global economy flowing.
Carbon emissions seem paradoxical. These engines burn dirtiest fuel, yet achieve 48% thermal efficiency, converting nearly half consumed energy into motion. Modern cars manage 25%. The efficiency comes from slow operation and massive scale, allowing effective heat recovery through turbochargers and economizers. Here's the secret we promised. Marine diesels burn fuel refineries would otherwise struggle disposing. That heavy fuel oil, thick, contaminated, full of sulfur, represents petroleum industry's bottom-of-barrel waste. Refineries initially paid ships to remove it. Marine engines transformed waste into commodity. Today, heavy fuel powers 90% of ocean shipping. Those engines burning waste move 60 billion tons of cargo annually, generating 3% of global carbon emissions, while handling 90% of international trade. From refinery waste to global commerce, the cycle completes. We've built machines so large they boggle comprehension, burning fuel so crude it seems impossible, moving cargo quantities that dwarf imagination. That container ship horizon, powered by controlled explosions in cylinders taller than you, spinning crankshafts heavier than your house, burning fuel thicker than syrup. Engineering at scale where normal physics seems inadequate, yet it works reliably, efficiently, endlessly. These aren't just engines, they're the beating hearts of globalization itself.
Under the hood of your car, there's a part the size of a fist, spinning at 200,000 revolutions per minute, in heat like a furnace, at speeds close to a jet engine. You've never seen it, and you won't, unless you tear apart the engine. Think horsepower is all about engine displacement? Wrong. And you'll never understand what's really pushing you forward during that pass. Now here's the weird part. Metal melted at 2,500 degrees, flowing like lava. And within weeks, this part is born from it, precise down to the thickness of a human hair. How? I'm about to show you. It all starts with a special heat-resistant alloy. Regular steel won't cut it here. Exhaust gases from diesel trucks and powerful vehicles can heat a turbine to temperatures where many metals start losing their strength. That's why they use complex nickel alloys with chromium, cobalt, and other elements added in. The alloy is melted in furnaces at temperatures over 2,500 degrees Fahrenheit. Inside the furnace, the metal glows bright orange and looks like liquid lava. Even a tiny impurity or air bubble can turn into a future crack. So quality control here is literally total. Next comes one of the most critical stages, casting. The molten metal isn't poured into an ordinary mold, but into special ceramic shells. The future turbine blades have a complex, curved shape. They must catch the exhaust gas flow as efficiently as possible while simultaneously withstanding enormous loads. The superheated metal, heated to over 2,500 degrees Fahrenheit, is prepared for pouring into the molds. But these aren't ordinary metal molds used for simple parts. The future turbine is cast in a special ceramic shell created specifically for a single product. First, they make a wax model of the turbine wheel. It already has all the future blades, curves, and channels. Then, they dip this model repeatedly into liquid ceramic slurry and coat it with fine sand. Layer by layer, a thick, hard shell builds up around the wax. When it dries, they melt out the wax, leaving behind a hollow mold accurate to within nearly a human hair. It's into this ceramic shell that they pour molten metal. The process looks stunning. Orange liquid flows through narrow channels and fills every curve of the future blades. And their shape is far from simple. If you look closely, they resemble twisted wings. This geometry is needed to capture the exhaust gas flow as efficiently as possible. After pouring, the metal slowly solidifies. Some facilities use controlled crystallization technology. Engineers literally control how crystals grow inside the metal. The reason's simple. A properly formed structure handles heat and vibration way better. Once the blank cools down, they destroy the ceramic shell. And here, for the first time, the future turbine appears, though right now it looks pretty rough. The surface is coarse and the geometry is still far from final. The next shop feels like a jewelry workshop for giants. Blanks get mounted into high-precision machines. Each blade is machined individually. Tolerances are measured in thousandths of an inch. If a blade's even slightly thicker or thinner than spec, the rotor balance gets thrown off. After casting, the turbine only vaguely resembles the finished product. Next comes the stage where the metal blank is refined to near perfection. I walk into the machining shop and everything looks like someone scaled up a jewelry workshop to factory size. Each turbine is secured in a high-precision machine. A computer controls dozens of cutting tool movements, gradually removing excess metal. It does this very carefully. In a single pass, the cutter can remove a layer thinner than a human hair. The blades get the most attention. They're the ones that take the hit from the hot exhaust gas stream. Every blade has the same shape, the same angle, and the same thickness. The machine moves between them with precision measured in thousandths of an inch. From the outside, it looks like a few thousandths of an inch difference between blades doesn't matter. But when the finished turbine starts spinning at over 200,000 revolutions per minute, even that tiny detail becomes a serious problem. An extra bit of metal creates imbalance. The rotor starts vibrating, bearing loads shoot up, and the entire assembly's lifespan drops. So after every machining stage, the part gets checked with measuring instruments. Laser scanners create a digital model of the turbine and compare it to the drawing. If even one blade falls outside tolerance, the part goes back for rework or gets scrapped entirely. This is where a rough casting transforms into a high-precision component that'll eventually withstand extreme temperatures, massive loads, and billions of rotations over its lifetime. After machining, the parts go through heat treatment. They're heated up and cooled down again, following a strictly defined schedule. This helps remove internal stresses that built up during casting and machining. But even after this, the turbine still isn't ready. Next up, quality control. And this is where it becomes clear why these parts cost so much. Every turbine gets checked for hidden defects. They use X-ray equipment for this. The metal literally gets scanned all the way through. Operators look for microscopic voids, cracks, or foreign inclusions. After the X-ray comes balancing. This is one of the most fascinating processes at the factory. The turbine is mounted on a specialized test stand and spun up to speeds that are almost impossible to imagine. For some models, that's over 200,000 revolutions per minute. Even an extra gram of metal at that speed becomes a serious problem. A computer detects the slightest imbalance, after which the operator removes a microscopic amount of material at precisely the right spot. Then the procedure repeats again and again until the parameters are perfect. And only now does the turbine make it to the turbocharger assembly. Here it's mated with the compressor wheel and shaft. In the finished unit, exhaust gases spin the turbine, which drives the compressor through a common shaft. The compressor pumps more air into the engine, and more air means more power without increasing engine size. That's why modern passenger cars increasingly use small turbocharged engines instead of large, naturally aspirated ones. And in the world of trucks, turbochargers became practically mandatory a long time ago. The scale of production is staggering. Major factories can churn out hundreds of thousands of turbos a year. Each one goes through dozens of inspections. From the moment metal melts to the finished part can take weeks. The funny thing is, drivers almost never see the result of all this work. The turbo hides deep under the hood. It doesn't gleam with chrome or turn heads in a parking lot. But this one small component often determines whether an engine has enough power to pass, climb uphill, or haul tons of cargo clear across the continent. And when you look at the entire process, from glowing hot metal to a finished rotor, you start to understand why turbine manufacturing remains one of the most complex branches of modern engineering. It's not enough to just cast a chunk of metal into the right shape. You need to create a component that will operate for years in an environment where the temperature resembles a furnace and the rotational speed approaches that of jet engines. And all of this so that every press of the gas pedal feels exactly the way the engineers intended. And to make sure you don't lose track of my channel, you should subscribe to it. Did you do it? See you then. 10,000 pounds of steel spinning at 2,000 RPM. If one end is heavier than the other by just half a pound, the engine tears itself apart from the inside. That's not an exaggeration. That's why a single crankshaft costs $200,000 and takes weeks to make. We start with a 45,000-pound ingot, run it through a 2,200-degree furnace and a 30,000-ton press. That shakes the floor like an earthquake. Final precision? 5/10,000ths of an inch, thinner than a human hair. One micro crack, and $200,000 goes straight to the scrap pile. I'm going to show you the entire process from the inside and explain why dozens of countries tried to copy this and ended up with nothing but scrap metal. It all starts with a massive steel ingot weighing about 45,000 pounds. Look at this chunk of metal. It looks like an unmoving mountain, but in just a few hours, it'll be going through absolute hell. For those looking into crankshaft manufacturing or how large engines are made, this stage is the foundation. We use special alloy steel with chromium, nickel, and molybdenum. These additives make the metal incredibly durable. This ingot gets shoved into a furnace where the temperature climbs to 2,250 degrees Fahrenheit. The steel turns bright orange, almost white with heat. The air around it shimmers, and even at 20 feet away, you feel your skin start to burn. This is the dangerous moment. Overheat the metal in the furnace, and it'll start burning from the inside out. Underheat it, and it'll crack during forging. Now we're looking at the star player on this floor, a gigantic forging press. Its force hits 30,000 tons. Think about that number. It's like every heavy tank in the country stomping on one piece of metal at the same time. When the press drops, the floor beneath our feet shakes like a 6.0 earthquake just hit. This machine literally crushes steel, forcing out every air bubble and compressing the crystal structure. That's exactly why forging steel under pressure matters so much. You end up with a part that's several times stronger than anything cast. This is where future crankshaft components take shape. The manipulator operator spins an 18,000-pound red-hot piece like it's a chopstick, but one wrong move could cost a fortune. After forging, the shaft looks rough, like some prehistoric monster covered in black scale. But now the real fun begins, precision machining. We move into the shop where massive lathes stand. A lathe like this can stretch up to 60 feet long. The shaft gets clamped into chucks and starts spinning slowly. Special tungsten carbide cutters bite into the steel, shaving off hundreds of pounds of excess metal in a single pass. Chips fly from the cutter, hot and razor sharp, falling like blue snakes into the trough. This is where we nail the dimensions. The journal diameter has to be accurate to within 5/10,000ths of an inch. That's way thinner than a human hair. If the machinist makes a mistake, the crankshaft for a truck will just seize up in the bearings from friction. A lot of people search for ship crankshafts or how engine factories work because the scale blows their minds. Look at these main and rod journals. They have to shine like mirrors. But being smooth isn't enough. The steel has to be incredibly hard on the outside, yet stay flexible on the inside so it doesn't crack from vibrations. That's where induction hardening comes in. A copper ring wraps around each journal, and we pump massive amounts of current through it. Within seconds, the metal surface heats up to 1600 degrees Fahrenheit and gets instantly doused with cold water. It looks dramatic. A cloud of steam fills everything around it, and the metal becomes hard as diamond to a depth of about a quarter inch. This is the toughest part of the engine, now ready for incredible testing. But there's one thing that can turn this perfect piece of iron into a pile of scrap: balancing. Think about it. This part weighs 10,000 pounds, and it's going to spin at 600, maybe even 2,000 RPM. If one end of the shaft is even half a pound heavier than the other, centrifugal force will literally tear the engine block to pieces. It'd be like a bomb going off inside the ship. So we put the shaft on a special balancing stand where a computer calculates every single gram of excess weight. The technicians carefully drill out the extra metal in the counterweights until the needle on the gauge goes dead still at 0. That's the moment of truth. When a giant like this spins absolutely silent with 0 vibration, that's a real engineering victory. Processing a single shaft like this can take several weeks. This isn't mass production where they're cranking out millions of parts. This is custom work for major projects. Every component gets its own passport, a document tracking each stage of its birth, from furnace temperature to X-ray scan results. We inspect the metal for microcracks using ultrasound and magnetic particle testing. If even a tiny void is hiding deep inside the steel, the entire shaft goes back to the melting pot. No repairs or welding allowed. What's at stake is the safety of massive ships carrying thousands of containers, or power plants that keep entire cities running. Right now we're watching the final polishing being applied to these finished crankshaft journals. They use special diamond-coated belts for this. The surface becomes so smooth, you can see a reflection in it like the finest mirror. This is necessary so the oil film between the shaft and bearing stays perfectly uniform. In a working engine, metal never touches metal. They're separated by a microscopic layer of oil. If the surface is even slightly rough, that layer breaks down and the engine dies in seconds. There's constant tension for these workers. When a 60,000-pound glowing billet floats overhead on a crane, you feel pretty small. But at the same time, there's pride. They know these crankshafts will be working somewhere in the icy Arctic waters or in quarry dump trucks in the mountains for the next 30 years. Interesting fact, the cost of one of these shafts can reach $200,000. And that's just the iron, without the engine around it. Now you understand why this business is so closed off. You need billions in investment just to build the facility and install presses like these. Plenty have tried copying these technologies, but without the metallurgy secrets and decades of experience, all they got was piles of broken metal. For those who want to dig deeper, search for marine crankshaft manufacturing, large-scale steel forging technology, and precision grinding of heavy components. These topics unlock a whole universe of engineering madness, where humans have learned to control the forces of nature with computers and hydraulics. At the end of our tour, we witnessed the finished product being wrapped in special anti-corrosion film and prepped for shipment. This shaft is heading to the other side of the planet, where it'll be installed in an engine as tall as a 3-story building. It's a breathtaking sight. We've traveled the entire journey, from a red-hot glowing ingot to a mirror-polished engineering masterpiece. It was a tough, scorching, and incredibly loud ride, but totally worth it. Hope you enjoyed this peek inside this metal cathedral. The world of heavy industry never stops blowing my mind with its sheer scale. Don't forget to check out my other videos about factories that make things you'd never see in everyday life. This was awesome, this was powerful, and this was real iron. Smash that like button if you felt the vibrations from that 30,000-ton press through your smartphone screen. See you on the next tour, where we'll definitely find something even more incredibly massive, expensive, and complex. Take care of your engines, and catch you in the next episode. Your transmission is made up of 800 parts, and a single error of 1/1000th of a millimeter on any of them means metal grinding instead of a smooth start. Most people think automatic is just convenient technology, but behind that quiet gear shift lies a manufacturing process where 1 degree of difference in a heat furnace ruins an entire batch of gears, where equipment costs as much as a house, and where one person is responsible for 1,000 parameters at once. I got inside one of these factories. I'll show you why these transmissions cost as much as real estate, and which one process even robots still can't replace. It all starts with the parts. Gears, shafts, clutches, valves, electronic modules. Each part arrives on its own schedule, sometimes from different countries. Picture a supply chain where every component is a tiny organism that has to play nice with the others. From the outside, the transmission looks compact, but inside, every element, each precise to within microns. For perspective, a micron is 1/1000th of a millimeter, or roughly 1/50,000th of an inch. When they say micron-level precision, it's not a metaphor, it's the standard. Assembly has several zones. First up is machining. Shafts and gears get cut on mills and grinding machines. Here it's not just about getting the right shape. You need to hit the right surface hardness and tolerances. A gear with the wrong profile will rattle and overheat. Then, heat treatment. Parts get hardened, tempered, sometimes coated for special protection, wear reduction. When the material behaves differently, even 1.5 degrees difference in the furnace can shift the characteristics. So temperature control here is like monitoring a patient's pulse. Next up, clean rooms. No, not as sterile as an operating theater, but dust here is enemy number 1. Where synchronizers and valves are involved, even a microscopic particle can trigger a jam. One reason these plants are rare, the need for expensive cleaning equipment, air filtration systems, special lines, special gloves and tools. Major investment. And that's why production concentrates in just a few places. Meanwhile, assembly runs parallel. Modern automatic transmissions aren't just mechanics, they're packed with lines of code and tiny control units. Electronics manage hydraulic pressure, gear engagement timing, and shift algorithms. Crucially, mechanics and electronics must play nice. Calibration after installation delivers that final chord of quality. If the electronics read wrong, the transmission will shift with a jerk or stick in one gear. It's both risk and scale. You're dealing with mechanics living in the real world and digital logic deciding in milliseconds. Main assembly. It's a blend of handwork and automated stations. The robots handle precision operations, pressing in bearings, torquing bolts to exact specifications, assembling modules using perfectly matched pairs. Humans do the detailed work, checking clearances, visually inspecting surfaces, performing operations that are tough to fully automate. Every transmission goes through testing on benches that simulate real-world conditions in a vehicle. Trial runs, heat cycles, load testing. On the test bench, a transmission runs for hours. They're checking shift feel, noise levels, fluid leaks. This is where hidden defects show up, things you'd never catch during assembly. If something's off, back it goes for disassembly and correction. Quality control? That's a whole different ballgame. They use instruments that measure shaft balance down to 1/10 of an ounce-inch, check surface roughness in microns, verify gears for profile accuracy. It's not cheap. The lab is basically a separate mini-factory with highly skilled personnel. Documentation is critical here. Every operation gets logged, parameters recorded. If a machine owner shows up a year later with a complaint, engineers can track down any part by serial number and check how it went through production. That's part of why these transmissions cost so much. Not just material costs, but the incredible level of control and tracking at every single stage. During the tour, they showed me one critical area, the grinding shop, where gears come out of the machines and head to final finishing. The smell of hot metal and oil hangs in the air, equipment hums, and at the same time, every operation is measured by laser scanners and ultrasound. They also do static shaft balancing in a clean room right there. An unstable shaft can cause vibration, and vibration at 10,000 RPM, that's a catastrophe. Tools lie on the floor next to the machine, but the master says, skill and experience matter more. Some things just can't be passed on through an algorithm alone. On the line, I watched dozens of parts come together to form a module. Several modules, and you've got a subassembly that then gets built into a housing. The transmission case sometimes weighs several dozen pounds and contains shafts, friction packs, planetary gears, and hydraulics. Planetary gears are their own kind of beautiful. Little satellites transferring torque, working in tight contact. If the clearance is even slightly off, the gear set whines and wears out fast. You need precision bearings here, and special fluid. The fluid formula matters. It handles pressure and heat, avoids foaming. Every little thing affects how long the transmission lasts. The risk in this business isn't just technical, it's economic. When you invest in a line, that's millions of dollars. One plant counts on thousands of transmissions a month, but the market can shift. A drop in demand or changes in vehicle standards can hit hard. Add geopolitics to that. Supplies of strategic materials, like high-grade steels or electronic components, can get stuck at customs. That's why not many companies take the risk of running the full production cycle. Toward the end of the tour, they let me peek into a back room with those same secret templates and tools. A few people are working on calibrating sensors, some scanning surfaces on a machine that costs as much as a house. One mistake, and an entire batch can go to waste. When a worker tells me 1,000 tiny parameters are riding on each task, I don't doubt it for a second. This is no place for carelessness. Walking back through the gates, I think about scale. Dozens of assemblies pass through this facility every single day, each one the result of years of development, engineering thought, and massive investment. You might not see these boxes while you're cruising down the highway, but when they leave this plant, they're a product of serious accountability. Next time you hear that quiet, tighter gear shift in your car, remember there are people and machines somewhere investing time and value to get it exactly right. When you look at this tangled maze of gears, channels, and valves, it becomes clear that assembling a transmission at the plant isn't some hobbyist's playground. It's a genuine test of nerves and high-precision equipment. Everything here hinges on fanatical attention to the tiniest details, because micron-level precision in manufacturing is the only law that cannot be broken without fatal consequences for the entire vehicle. If you've ever wondered how to build an automatic transmission, the answer lies in these 800 individual parts, each one needing to slot perfectly into place on the first try without any unnecessary friction. A lot of people ask why expensive transmissions cost as much as a small house in the suburbs, but just look at these tolerances. An error of 1/1000th of an inch instantly turns your smooth launch into a series of horrifying jolts and metallic grinding. The final bench testing of automatic transmissions is the moment of truth, where every hydraulic valve has to fire within milliseconds under 300 pounds per square inch of pressure, or else this entire iron brain will simply burn itself out from the inside within the first mile down the road. There are parts in cars nobody thinks about, until they break down in the middle of the highway at 3 in the morning with a fully loaded trailer. The axle and differential, those are exactly such parts. They hide under the frame, covered in dirt and grease, and over the entire service life of a truck, they might not get any attention except for an oil change once a year. But it's through them that torque passes from the engine to the wheel. On a heavy highway tractor, this torque can reach 5,000 pound-feet. For comparison, a sporty Porsche 911 puts out 350 to 400 pound-feet, and it's very powerful. In other words, through one rear truck axle passes loads 12 to 14 times greater. And this part cannot fail. At all. Ever. The plant where I'm at is Dana Incorporated in Fort Wayne, Indiana. They make axles and differentials for heavy-duty pickups like the Ford F250 and F350, for buses, for construction equipment, and for semi-trucks. Manufacturing axles and differentials for heavy machinery is a narrow specialty, and the serious players in this niche across all of North America you can count on one hand. The barrier to entry? Several $100,000 in equipment and years perfecting the technology. Most companies just buy finished axles instead of trying to make them in-house. We start with the axle housing, that same crosswise tube you see under the rear end of a pickup or truck. On light vehicles, it's stamped from sheet steel and welded together. On heavy ones, it's cast or forged. For rear axles, they cast the housing from ductile iron or steel in a sand mold. And one such casting, after machining, weighs anywhere from 120 to 280 pounds, depending on load capacity. A sand mold isn't what you think. It's not just holes in the sand. The mold is made from a special mixture of silica sand and resin, which gets packed into a metal box and baked in an oven. The accuracy of such a mold is plus or minus 60 thousandths per foot of length. Sounds rough, but for a casting that then goes to machining, it's plenty. After casting, the housing goes to the lathe and milling machine. The bearing seats are bored out. Threaded holes for the differential case mounting are cut with precision that guarantees uniform tension on all bolts during assembly. Then the housing goes to wash. A stream of cleaning solution at 80 pounds per square inch blasts out all the chips and sand left over from casting. If even one tiny chip stays inside and gets into the oil, it'll destroy a bearing in a few thousand miles, and nobody will figure out why. Now the main pair, the ring gear and pinion gear. This is where what separates serious axle manufacturing from everything else begins. These two gears transmit torque from the drive shaft to the differential and onto the wheels. Their teeth are cut at an angle. This is a hypoid pair, where the axes of the two gears don't intersect but pass each other in space. This exact geometry allows lowering the drive shaft and reducing the tunnel in the cabin, and it's precisely what creates a contact geometry that's simultaneously the zone of maximum load and maximum sliding, meaning the most hostile environment for any gear tooth. Ring gear blanks are forged from alloy steel, the traditional chromium, nickel, and molybdenum formula. A ring for a heavy-duty axle has an outer diameter between 14 and 22 inches, and weighs anywhere from 25 to 60 pounds. The forging goes to a lathe where they remove the black scale allowance, then to a gear hobbing machine. The spiral bevel tooth is cut by a cutter head that simultaneously rotates and moves along a complex spatial path. A single pass on one tooth takes 2 to 4 seconds. A ring gear for a heavy-duty axle has 38 to 48 teeth, and the entire cutting cycle runs about 3 to 4 minutes per part. After cutting comes heat treatment, carburizing in a carbon-rich gas atmosphere at 1700 degrees Fahrenheit for 4 to 8 hours. The tooth gains a hard, wear-resistant surface layer 35 to 60 thousandths of an inch thick, while keeping a tough core that absorbs impact loads without cracking. Grinding the teeth after hardening is the longest and most precise step. The grinding machine passes over each tooth and brings the final profile to within plus or minus 0.2 of a mil on tooth thickness. For parts transmitting 5,000 pound-feet at 1,000 RPM, this precision isn't overkill. It's exactly what's needed so the teeth contact across the proper area, not at the edge or center. Miss by 3 mils in the profile, and under load, the contact patch shifts and the tooth breaks on the very first loaded cycle. After grinding, they check a gear pair, the ring and pinion, together for a contact pattern. The gears are coated with a special paste, rolled under 5 to 10 pound-feet of load, and inspected to see where marks appear on the teeth. The pattern should be in the central zone of the tooth, not running to the edge, and it should have a specific shape, depending on the gear type. If the pattern's off, the pair goes back for adjustment or gets scrapped. A good inspector reads that pattern as confidently as a dentist reads an X-ray. The differential is a mechanism inside the axle housing that lets the left and right wheels spin at different speeds through turns and over uneven ground. For a heavy truck or bus, the differential carries extra loads. When one wheel's on ice and the other's on asphalt, the torque difference between them can hit 1,000 to 1,500 pound-feet. The differential case is, again, a ductile iron or steel casting, with 4 or 6 spider gears inside. The spiders are small bevel gears, 1 to 2 inches in diameter, but their load per unit of tooth area is among the highest of any gear in the vehicle. They're also case-hardened, heat-treated, and ground. Axle assembly is a job that both robots and people do together at this plant. A robot installs the bearings into the housing with an interference fit of 1 to 2 mils, presses them in with 2,000 to 5,000 pounds of force. A human sets the adjusting nuts and dials in the preload on the main pair's bearings, a critical parameter that determines the service life of the entire axle. Too little preload and the bearings rattle and wear out in a few tens of thousands of miles. Too much and they overheat and fail in the same time frame. The window between too little and too much is 2 to 4 mils of axial play, measured with a dial indicator right there on the assembly stand. After assembly, each axle goes to a break-in test stand. It's spun for 10 to 20 minutes at various speeds and loads while measuring bearing temperature and noise levels. Noise is measured with a microphone in a soundproof chamber and compared against a reference spectrum. A characteristic howling sound, the so-called wolf frequency, indicates improper contact pattern or deviation in tooth profile. If the microphone picks it up, the axle gets disassembled and the cause is found. Because on the road, that sound will only get worse, and the problem won't just disappear on its own. At final inspection, samples from each batch are pulled and completely disassembled. Gear teeth are measured, bearings are removed and their condition checked after break-in. Contact pattern is verified once more. If they find anything that shouldn't be there, the entire batch gets stopped and every axle is analyzed. Poor installation when mounting on the vehicle, or the wrong oil. The axles themselves? Rock solid. Because a part that's made this entire journey, from casting to the test stand, leaves the factory with enough margin to survive 1,000,000 miles under load. That's roughly the lifespan of a heavy-duty axle with proper maintenance. 1,000,000 miles. That's 20 trips around Earth's equator. Hit subscribe. The next facility is already queued up, and it's even more massive. Drop a comment with where you're from. Maybe next time I'll swing by your neck of the woods.
Every year, millions of semi-trucks hit American roads, and each one rides on 18 wheels. A wheel seems like just a wheel, but I'm standing here at the Alcoa plant in Cleveland, Ohio, and I can tell you, what happens to a chunk of aluminum in this place is one of the most spectacular shows in heavy industry I've ever seen. Let's start with a question most people never ask. Why aluminum in the first place? A truck is a machine that only makes money when it's moving, and every extra pound of its own weight, that's one less pound of cargo it can legally haul. In the US, the maximum gross vehicle weight for trucks on federal highways is 80,000 pounds. That's the law. So if the truck weighs more, it hauls less. And if it hauls less, it earns less. The math is simple. A steel wheel for a heavy-duty truck weighs about 40 pounds. A forged aluminum wheel, roughly 29 pounds. The difference? 11 pounds per wheel. Across 18 wheels, that's nearly 200 pounds. 200 pounds that can be converted into 200 pounds of additional cargo. Multiply that by hundreds of trips per year, and the difference in revenue becomes very real. That's why aluminum. But there's a catch. Aluminum is a soft metal. A truck wheel lives in conditions that would break most metals pretty quickly. Pounding from uneven roads, constant load from tens of thousands of pounds of cargo, heat from the brakes, temperature swings from -20 to over 100 degrees Fahrenheit and beyond. A simple cast aluminum wheel can't handle that. It just isn't strong enough. That's why wheels are forged. Forging is a process where the metal doesn't just take shape, it changes its internal structure. Under enormous pressure, the metal grains reorganize, compress, align. Forged aluminum is stronger than cast aluminum, roughly the same way an oak plank is stronger than pressed particle board. They look similar on the outside, completely different on the inside. It all starts with a billet. An aluminum billet is a cylindrical chunk of alloy, kind of like a thick, short log. Diameter, about 12 inches, height, also around 12 inches, weight, roughly 50 pounds. The material isn't pure aluminum, but a 6000 series alloy, which includes magnesium and silicon alongside aluminum. It's this combination that delivers the right balance of lightness, strength, and forgeability. The billet gets loaded into a furnace and heated to around 800 degrees Fahrenheit. That's below aluminum's melting point. The metal doesn't flow, it stays solid. But at this temperature, it becomes plastic, almost like softened modeling clay. That's the exact state it needs to be in under the press, not sooner and not later. If the billet cools even a few dozen degrees more than it should, it becomes stiffer, and the forging won't go right. That's why the billet moves fast from furnace to press. And now it hits the press. A hydraulic press with 8,000 tons of force. 8,000 tons! That's roughly the weight of 65 fully loaded semi-trucks stacked on top of each other. All that force concentrates on a single billet 12 inches in diameter. The press descends, it takes a fraction of a second. The glowing hot billet that just looked like a cylinder spreads into a disc in one blow. The metal literally explodes outward, filling the mold. Sparks of scale and steam fly from under the press. The part that was just a rough cylinder now has the recognizable contours of a wheel. The hub in the center, the disc, the rim. All this in one stroke, in 1 second. I watched this several times in a row, and each time I couldn't believe how fast it happens. You expect some long process and suddenly bam, and there's a wheel. More precisely, a wheel blank, but the shape is already there, and it appeared instantly. After the first strike, the workpiece isn't done yet. It's heated again and placed under the press a second time for what's called finish forging. This blow refines the geometry to tighter dimensions, smooths out imperfections from the first forging. After 2 strikes, the workpiece already looks a lot like a finished wheel, but it still has excess metal squeezed out between the die halves. That gets trimmed off in a special die, and the workpiece takes on a clean contour. Now comes heat treatment. This is a stage that's invisible but critically important. The workpiece is heated to a specific temperature, held there, then rapidly cooled in water. That's called quenching. Then comes aging, heating to a lower temperature and a long hold. This entire sequence changes the alloy's microstructure at the molecular level. Magnesium and silicon atoms form tiny hard particles that strengthen the aluminum matrix. After heat treatment, the wheel can handle loads that would tear apart an untreated blank. After heat treatment, the wheel heads to machining. CNC lathes and milling machines remove material from precision surfaces: the tire bead seat, lug bolt holes, hub face surfaces. Tolerances here? Thousandths of an inch. The tire must sit on the wheel with 0 gap and 0 interference, exactly as engineered. Lug bolts must enter their holes without play. Any deviation in the wheel either won't install or will wobble at speed. Speaking of wobble, one of the most critical tests on a finished wheel is run-out check. Deviation from a perfect plane and circle. The wheel gets mounted on a specialized fixture and spun. Sensors measure how much the surface deviates from the theoretical ideal. If the wheel runs out even a few hundredths of an inch beyond spec, it goes back for rework or gets scrapped. A semi rolling at 75 miles per hour with 45,000 pounds of cargo doesn't forgive wheel runout. Final stage, polishing. Alcoa makes wheels that look like mirrors. This isn't just aesthetics, it's part of the product and part of the marketing. Truck drivers in America take the appearance of their rigs seriously, and a shiny wheel is a sign of quality and pride. Polishing happens in multiple stages with progressively finer abrasives, and by the end the surface reflects your face better than an ordinary bathroom mirror. The finished wheel goes through final inspection, dimensional checks, run-out testing, visual examination, and then to the warehouse, from there to dealers and truck assembly plants across the country. From billet to finished wheel, a few hours of production time and several days counting heat treatment. The result? 29 pounds of forged aluminum that'll serve 1 million miles and more. The finished wheels leave Cleveland for every corner of the country. Some head straight to assembly plants, Kenworth, Peterbilt, Freightliner, Mack, where they're built into new semi-trucks. The rest get distributed to parts dealers from Florida to Washington, because wheels on working rigs wear out too and need replacing. Turns out the Cleveland plant feeds the whole country. both new trucks and those already racking up miles on the interstates. That's the story of one wheel, from a red-hot billet under an 8,000-ton press to the highway somewhere between Texas and California. If you're into watching how the stuff we don't notice actually gets made, subscribe to the channel. There are plenty more stories like this one. I want to say something separate about changing a wheel on the road, because it's not the same as swapping a tire on a sedan by the shoulder. On a semi-truck, wheels last a long time, but when one finally gives out, it's a whole different procedure. First off, the wheel weighs 29 pounds, not something one guy easily spins with one hand. Second, the lug bolts are torqued to 450 to 500 pound-feet. For comparison, on a regular passenger car, it's about 100 pound-feet, meaning the bolt on a semi is tightened 4 to 5 times harder, because underneath that wheel could be 80,000 pounds of cargo moving at 70 miles per hour. There's no room for a loose bolt. That's why the swap is done with a calibrated torque wrench by protocol, and after the change, the wheel is mandatory rechecked after a set number of miles. Simple part, but behind it stands an entire engineering culture.
Every second, 32 tires begin service worldwide. Each survives 100,000 miles of punishment, heat, friction, road impacts before replacement. Picture mountains of rubber growing daily. 2 billion tires manufactured annually, weighing 25 million tons combined. That's every car, truck, aircraft, and bicycle on Earth demanding fresh rubber constantly. How does liquid petroleum become indestructible black donuts? Why do old tires refuse to decompose for 500 years? Stick around. You'll discover the shocking chemical process transforming oil into immortal rubber, and the jaw-dropping secret of where 85% of American worn tires end up. Hint? It's beneath your feet on football fields.
The story begins in Southeast Asian plantations, where rubber trees grow in geometric rows, stretching miles. Workers cut V-shaped grooves into bark, collecting milky latex sap in cups. Each tree produces 2 ounces daily, barely enough to fill shot glasses. Natural rubber comprises 30% of modern tires. The remainder uses synthetic alternatives derived from petroleum. Massive chemical plants crack crude oil into monomers, butadiene, styrene, then polymerize them into synthetic rubber matching natural properties. These facilities process 50,000 barrels daily, transforming black liquid into white crumb rubber. The similarity is uncanny. Petroleum-based rubber exhibits elasticity, strength, and durability rivaling million-year-old tree evolution. Chemistry replicates nature in months.
Next comes compounding, the secret sauce where rubber meets additives. Industrial mixers, standing 2 stories tall with rotors spinning at 80 RPM, blend rubber with carbon black, silica, sulfur, accelerators, and antioxidants. Carbon black, basically controlled soot production, reinforces rubber while providing characteristic black color. Without it, tires would be translucent white and fail within miles. Each tire compound contains 15 ingredients mixed in precise ratios. Tread rubber emphasizes durability. Sidewall rubber prioritizes flexibility. Inner liner uses butyl rubber for air retention. Formulations remain trade secrets. Michelin's compounds differ from Goodyear's, creating performance variations. Mixing takes 12 minutes at temperatures reaching 300 degrees Fahrenheit. The batch, weighing 500 pounds, emerges as uniform black mass ready for shaping.
Giant extruders force hot rubber through dies, creating continuous strips of tread, sidewalls, and bead filler. These machines operate like industrial Play-Doh shapers, pushing material through shaped openings at forces exceeding 2,000 psi. Tread emerges with grooves preformed. Sidewalls arrive as smooth sheets. Cooling conveyors solidify the profiles. Meanwhile, calendaring machines squeeze rubber sheets to precise thickness, measured in thousands of inches, coating steel cord and fabric plies. These textile layers provide structural strength. Modern radial tires contain steel belts running at 0 degrees to rotation direction, fabric plies at 90 degrees, creating cross-brace architecture. Workers cut these components into precise lengths, stockpiling thousands of parts daily for assembly lines demanding continuous supply.
Comes tire building. Robotic ballet assembling 30 components into recognizable shapes. Cylindrical drums rotate while automated arms apply inner liner, body plies, steel belts, sidewalls, and tread in programmed sequence. Each component positions within 0.05-inch tolerance. Precision matters because imbalance at highway speeds creates dangerous vibrations. The green tire, uncured assembly, looks puffy and pale, lacking final tread pattern. Steel beads, wire bundles coated in rubber, anchor edges, providing mounting surfaces for wheel rims. These beads contain piano wire strength steel wound in continuous loops. Braking beads requires forces exceeding 5 tons, ensuring tires never separate from rims even during blowouts. Assembly takes 3 minutes per tire on modern automated lines, producing 2,000 tires daily.
Curing transforms green tires into finished products through heat, pressure, and chemistry. Massive presses, resembling medieval iron maidens, close around green tires. Internal bladders inflate with superheated steam at 350 degrees Fahrenheit and 200 psi. External mold segments, engraved with tread patterns, press inward simultaneously. This step is critical. Vulcanization. Sulfur atoms cross-link rubber polymer chains, creating three-dimensional molecular networks. Picture chain-link fences welded together at every intersection. That's vulcanized rubber at molecular level. The process, discovered accidentally by Charles Goodyear in 1839, transformed useless sticky material into engineering marvel. Curing takes 12 minutes. Afterward, tires emerge rigid with crisp tread patterns and permanent shape. They'll never soften or melt again. Vulcanization is irreversible.
After curing, quality control begins. X-ray machines scan internal structure, detecting steel belt misalignment, air pockets, or ply separations invisible externally. Uniformity machines spin tires at highway speeds, measuring force variations. Even 0.5-pound imbalance causes rejection. Ship tires must perform flawlessly at 120 miles per hour for tens of thousands of miles. Inspectors examine tread depth, sidewall finish, bead seating. DOT codes stamped into sidewalls identify manufacturing plant, date, batch number, critical for recalls. Modern tires undergo durability testing. Machines simulate 50,000 miles in 72 hours, cycling through temperature extremes, overloading, underinflation. Failure rate must stay below 0.1%. That's one defective tire per 1,000, because tire failure at highway speeds kills people. Performance testing pushes limits beyond consumer use. Test drivers race prototype tires on proving grounds, executing emergency maneuvers, sustained high-speed runs, extreme weather conditions. Sensors measure temperatures, pressures, wear rates. Data feeds computer simulations refining compounds and construction. Winter tires use softer compounds, remaining flexible below freezing. Summer tires employ harder rubber, resisting heat degradation. All-season compromises performance for year-round versatility. Racing slicks sacrifice tread patterns for maximum contact area. Professional race tires last 200 miles but provide grip exceeding street tires tenfold. Tire engineering optimizes contradictory requirements: durability versus performance, comfort versus handling, cost versus longevity.
Every design represents compromises, balancing physics against economics.
This technology evolved from crude beginnings. Ancient Mesoamericans harvested rubber for balls and waterproofing 3,000 years ago, but material degraded rapidly. Charles Goodyear's 1839 vulcanization discovery changed everything. Accidentally dropping rubber sulfur mixture on hot stove created heat-stable material. The pneumatic tire emerged in 1888 when John Dunlop invented air-filled rubber tires for his son's tricycle. That innovation enabled automobile revolution. Cars needed shock absorption only inflatable rubber provided. Radial tire construction, invented by Michelin in 1946, improved durability 50% over bias ply designs. Today's run-flat tires, self-sealing compounds, and airless prototypes continue evolution. Annual global production exceeds 2 billion units, creating waste management crisis demanding solutions.
Carbon emissions dropped by 62% using recycled tire crumb versus virgin rubber production. Industry saves over $41 billion annually through tire recycling. Processing old tires into crumb costs 70% less than manufacturing new rubber from petroleum. So here's the secret. 85% of American-worn tires avoid landfills through recycling programs. Shredders reduce tires to fingernail-sized crumb. This material becomes artificial turf infill, those black granules beneath football field grass that cushion impacts and improve drainage. Schools, parks, and stadiums nationwide walk on recycled tires daily without knowing. Crumb rubber also creates playground surfaces, running tracks, asphalt modifiers, improving road durability 20%. From petroleum to pavement to playing fields, cycle completes. Tires never die. They transform. That indestructible black donut refusing decomposition becomes humanity's accidental gift to circular economy. We've learned that immortal materials demand eternal responsibility.
Every year, billions of people around the world press the same pedal, and they don't even realize it was slowly killing them for decades. What was supposed to save lives quietly filled the air with poison. Why did a material once considered perfect vanish almost overnight? And what replaced it? There's one detail brake pad ads never mention, but it's what determines whether your car stops in that critical split second. Today, these pads withstand hell itself, don't smoke, and leave barely a trace. But the road here was deadly dangerous. Stick around till the end, and you'll discover which hidden component once cost millions of lives and why modern factories guard their formulas like state secrets. In the 1920s, every brake pad contained asbestos, fibers that could handle 1,500 degrees Fahrenheit and wouldn't wear out. But every tap of the pedal released microns of poison into the air, settling in the lungs of drivers and pedestrians. By the 1990s, asbestos had killed millions. Lung cancer, mesothelioma. Europe banned it first in 1998. Manufacturers scrambled to find a replacement, organic compounds made from rubber, glass, and metal fibers. The first non-asbestos pads braked worse, overheated at 750 degrees, and released the rotor. But it was a start. Today, the top choice is ceramic composites. The base is ceramic made from silicon nitride and silicon carbide, mixed with copper fibers for heat dissipation. The material withstands 650 degrees without deforming, doesn't squeal, and doesn't dust. Ceramic makes up 40 or 50% of the mass, reinforced with steel fibers for strength. At 500 degrees, regular pads smoke. Ceramic ones stay cool as ice. In this massive plant, something is born that'll save your life on the road. Manufacturing ceramic brake pads isn't just mixing powder with binder. It's precise science involving pressure, fire, and high-precision machinery. Each pad weighing 7 ounces has to survive 600 degrees of hell, not crumble, and not let go of the rotor. Let's break down the process step by step, from raw materials to finished kit. Everything starts with hoppers full of powders. The main ingredient, ceramic, meaning silicon nitride silicon carbide, a white powder hard as diamond. They add copper fiber for heat dissipation, thin threads the width of a hair, graphite for smooth grip, reinforced glass for strength, barium sulfate for stability at high temperatures. Each recipe is a factory secret, like the Coca-Cola formula. In giant mixers with a 500-gallon capacity, powders are combined in precise proportions. They add liquid wax-based lubricant, 5 or 7% by weight. The mixer spins for 30 minutes at 50 revolutions per minute, transforming dry powder into a uniform wet mass, like bread dough. Temperature is held at 100 degrees so the lubricant doesn't freeze. The result is raw dough weighing 1,100 pounds, ready for forming. The mass goes into a rotary press, a machine with 20 tons of force. They pour 550 grains of the mixture into a metal mold measuring 6 by 2.5 by half an inch. The top plate descends with 285,000 pounds per square foot of pressure, like parking a tank on your palm. In 10 seconds, the dough compresses into a monolithic green blank, 3/4 of an inch thick. The pressure squeezes out all the air, creating a density of 175 pounds per cubic foot. The press runs in cycles, 60 blanks per hour. Each comes out perfectly smooth with a friction surface angled at 5 degrees for better disc contact. The blank's still brittle as cheese, but it already has the shape of the future pad. The most critical stage, sintering. Green blanks go onto steel trays, 50 pieces each, then get pushed into a tunnel kiln 100 feet long. Temperature rises gradually. At peak heating, 4 hours in, the ceramic melts. Copper fibers fuse. Graphite crystallizes. Total sintering time, 12 hours. Finished pads, gray-silver monoliths. Go to inspection. A laser scanner checks dimensions accurate to 1/100th of a millimeter. Ultrasound checks density and cracks. 2% get rejected. Next, grinding. The machine removes 0.5 millimeter from the friction surface for perfect geometry. Edges get rounded to prevent squealing. They apply a protective coating, a thin layer of molybdenum disulfide for that first soft breaking. Laser marked, then assembled into kits, 4 pads plus springs plus backing plate. The final test, the simulation stand. The pad is pressed against a disc spinning 2,000 revolutions per minute for 200 cycles. Acceleration, then hard braking up to 6,000 degrees. They check wear, squealing, dust. Ceramic pads pass without smoke. Metal ones squeal. A finished pad wears out after 30,000 miles. That's normal wear. With aggressive driving, it wears out after 18,000 miles. The U.S. market operates with 131 facilities, which has decreased by 0.6% in recent years due to automation. Production is tied to the automotive industry. Rising car sales drive demand, especially for pad replacements in trucks and passenger vehicles. Key trends: shifting to eco-friendly materials without copper. California capped it at 0.5% starting in 2025, which cut pollution by 28% statewide. Imports matter, but tariffs affect local production. The leaders are the southern U.S., specifically Texas, Alabama, Tennessee, with Ford and GM plants. The European brake pad market shows steady growth at an average annual rate of 4.7% through 2028. In Germany, the market leader volume will hit nearly $320 million by 2028. France is growing at 5.5% annually, the UK at 3.8%. Metallic pads are still popular and hold 25% of the EU market because they're cheap for trucks and Porsches. But their dust is a problem. Steel and copper settle on roads, get into water and lungs. Ceramic cuts emissions by 80% compared to these semi-metallics. Now, besides asbestos and metallic pads, there was an attempt to make organic ones. These are pads from the 2000s, the first mass replacement for asbestos. The base is synthetic rubber, fiberglass for reinforcement, Kevlar or aramid fibers for strength, plus barium sulfate and graphite. The soft compound gave a quiet bite. Little dust, didn't scratch rotors. But at 550 degrees, they lose 30% of their stopping power, which works for daily driving but not for sport.
Slam a hammer into your windshield. The glass spiderwebs but holds together, cracks spreading like frozen lightning, yet staying in place. Now hit a side window. It explodes into 10,000 tiny cubes, flying everywhere. Same material, radically different behavior. Every year, factories produce 500 million automotive glass panels worldwide. That transparent barrier between you and highway speeds represents chemistry and physics pushed to extremes. How does molten sand become safety glass? Why does windshield glass behave opposite of side window glass during impact? Stay with us. You'll discover the counterintuitive process where breaking glass makes it stronger, and the shocking secret of the plastic film sandwiched invisibly between windshield layers, the unsung hero preventing decapitation during crashes.
Our story begins not with glass, but with sand. Silica sand mines in places like Missouri and Wisconsin extract incredibly pure quartz, 99.8% silicon dioxide. The purity matters obsessively. Just 0.01% iron content tints glass greenish. Modern automotive glass requires absolute clarity, demanding sand so pure it resembles white powder rather than beach grit. Walk a glass plant raw material yard. Mountains of sand sit beside smaller piles of soda ash, limestone, and dolomite, the recipe unchanged for centuries. Automated systems measure ingredients to within grams per ton. One batch mixer explains, sand is main ingredient, but the additives determine everything: melting temperature, strength, thermal expansion. Get ratios wrong and glass cracks cooling from furnace or shatters first bump on road.
The furnace is where sand dies and glass is born. Temperatures inside reach 2,700 degrees, hot enough to melt steel. The mixture feeds continuously into one end, while molten glass flows out the other. Inside, sand grains disintegrate, their crystalline structure collapsing into amorphous liquid. Silicon, oxygen, sodium, and calcium atoms swirl in chaotic dance, losing all memory of original form. Picture the furnace operation. It runs 24/7 for 15 years straight. Stopping means the furnace cools. Glass solidifies inside, requiring complete demolition and rebuild, costing tens of millions. Operators monitor oxygen levels constantly. Too much air oxidizes refractory bricks lining furnace. Too little, glass contains bubbles. The molten glass glows orange, viscous as honey, ready for shaping.
The float process creates perfectly flat glass, invention revolutionizing industry in 1959. Molten glass at 2,000 degrees pours onto molten tin bath. Tin remains liquid at these temperatures, yet denser than glass. The glass literally floats, spreading across tin surface under gravity, achieving perfect flatness naturally. Physics does what human hands never could, create distortion-free sheets. Watch the float bath. The glass ribbon, still glowing red, stretches 300 feet across the tin. Controlled atmosphere prevents oxidation. Rollers pull the glass forward at precise speeds, determining thickness. For automotive glass, thickness reaches 0.18 inches for windshields, slightly thinner for side windows. The glass gradually cools as it travels, solidifying while maintaining molecular randomness. No crystals, no grain structure, pure frozen liquid.
Now comes cutting. The continuous glass ribbon, cooled to room temperature, gets scored by diamond-tipped wheels. The cutting happens fast. Automated systems follow computer patterns, scoring complex windshield shapes in seconds. Pressure applied to scored line causes glass to snap cleanly. Skilled cutters once did this manually, taking minutes per piece. Modern systems process one windshield every 6 seconds. But raw glass is dangerous. Sharp edges could slice arteries. Grinding wheels smooth every edge, creating slight bevel preventing cuts. Then, washing. Automotive glass undergoes cleaning process NASA would envy. Deionized water rinses away particles. Even microscopic contamination shows up later. One speck of dust between windshield layers creates bubble visible to driver, requiring part rejection. Cleanliness isn't preference, it's requirement.
Tempering transforms side and rear windows into safety glass through controlled violence. Glass pieces enter furnaces heated to 1,300 degrees, just below melting point. The glass becomes plastic, molecules mobile yet solid. Then comes the quench. Jets blast cold air across both surfaces simultaneously. The outer layers cool and solidify instantly, while interior remains hot. This creates locked-in stress. Outer surfaces compress, while interior stretches, like tightening rubber band inside rigid tube. The tension is enormous. Tempered glass achieves 4 times the strength of regular glass. But here's the crucial part. When stressed beyond limits, that internal tension explodes the glass into thousands of small cubes. The pattern isn't random, it's designed. Those dice-sized pieces have dull edges, reducing laceration injuries. One safety engineer puts it bluntly, tempered glass doesn't cut throats. That's the whole point.
Windshields require a different approach, lamination. 2 glass sheets sandwich a plastic film called PVB, polyvinyl butyrol. This clear film, thinner than credit card, performs miracles during crashes. The glass sheets go through gentle heating, softening slightly. Then into the autoclave, pressure vessel combining heat and pressure. Picture autoclave loading. Workers stack 50 windshields on racks separated by spacers. The door, thick as bank vault, swings closed. Temperature rises to 250 degrees while pressure climbs to 200 psi. Under these conditions, PVB melts slightly, flowing into every microscopic gap between glass and film. Chemical bonds form. After 90 minutes, the layers become inseparable. What exits is single unit, glass-plastic glass sandwich, impossible to separate without destroying.
The PVB layer's genius reveals itself during impact. When windshield hits something, rock, bird, human head, the glass fractures, but PVB holds fragments in place. The windshield spiderwebs but doesn't collapse. During rollover accidents, that intact windshield prevents roof-crushing occupants. In frontal impacts, it keeps airbag deployment controlled, providing surface for airbag to push against. Modern windshields incorporate additional tech. Acoustic PVB layers dampen road noise. Heated windshields use transparent conductors embedded in glass, microscopic wires invisible to eye but conducting electricity, melting ice. Some luxury cars use infrared reflective coatings, reducing cabin heat by 40%. That simple windshield contains 7 layers, 2 glass, 3 PVB interlayers, and 2 coatings, each serving specific function.
Safety glass emerged from accidents. In 1903, French chemist Edouard Benedictus accidentally knocked flask off shelf. The glass shattered but held together, coated inside with cellulose nitrate residue. He recognized implications for automobiles. Early windshields were flat plate glass, killing occupants during crashes. But public pressure and regulation forced change. World War II accelerated development. Military needed shatter-resistant cockpit canopies. Post-war, automotive glass became sophisticated. Curved windshields arrived in 50s, requiring precise heating and forming. Tinting followed in 60s. Today's windshields represent billion-dollar research, material science, chemistry, and engineering converging in that transparent shield you barely notice.
Carbon emissions drop 38% using recycled glass versus virgin sand. Industry recycles 12 million tons of automotive glass annually. Processing cullet, recycled glass, requires 25% less energy than melting raw materials. Here's the secret we promised. Windshield and side window behave differently by design. Laminated windshield must hold together. Its job is containment during crash, keeping occupants inside, maintaining structural integrity. Tempered side windows must shatter. Their job is escape. During submersion or fire, occupants need exit path. Tempered glass shatters easily from inside, allowing escape. Wrong glass and wrong location kills people. That difference isn't accident. It's calculated engineering saving lives daily. From sand to safety, the cycle completes.
We've learned that best protection sometimes means braking in a controlled way. That windshield isn't just keeping wind out, it's a sophisticated safety device engineered through centuries of tragedy and innovation. The glass between you and highway could be all that stands between minor accident and fatal ejection. We barely notice it, which proves it's working exactly as designed. Transparency isn't the achievement. Staying invisible while performing miracles, that's automotive glass mastery.
A lot of you have been asking in the comments about aluminum. Why it's so light, why it melts at a relatively low temperature, and where it even comes from in the first place. Today we're going to trace aluminum's entire journey, from red clay in the jungle to shiny foil in your kitchen. I'm standing right now next to a bauxite mine in Australia, and trust me, what you're about to see will completely change how you think about this metal. Look at this red rock in my hands. This is bauxite, the ore we make aluminum from. Looks like ordinary clay, right? But hidden inside is a metal that changed the world. Bauxite is made mostly of aluminum oxide, also known as alumina. The problem is, aluminum is bonded so tightly to oxygen that breaking that bond is incredibly difficult. So difficult that until the 19th century, aluminum was more expensive than gold. I'm standing right now on the edge of an open-pit mine, 300 feet deep and over a mile wide. Massive excavators with buckets the size of a bus dig bought it from the depths. Each bucket lifts 30 tons of rock at a time. In one day, a single mine extracts about 50,000 tons of bauxite. The rest is iron, silicon, titanium, and other impurities. The extracted bauxite gets loaded into trucks, each hauling 200 tons, and driven to the processing plant. This is where the first stage begins, called the Bayer process. It was invented by Austrian chemist Carl Bayer way back in 1887, and the principle hasn't changed much since. Look at these giant tanks, each one as tall as a 5-story building. Inside, bauxite gets mixed with caustic soda, a 30% concentrated alkali. Temperature, 300 degrees Fahrenheit. Pressure, 30 pounds per square inch. Under these conditions, aluminum oxide dissolves in the alkali, while the impurities stay solid. The process takes 8 hours. Then the mixture gets filtered through massive filters. The liquid containing dissolved aluminum oxide moves forward, while the solid waste stays behind. This waste is called red mud, and it's one of the biggest environmental problems in the aluminum industry. For every ton of aluminum produced, 1.5 tons of red mud forms. A caustic red sludge that has to be stored somewhere. I'm standing right now next to a red mud settling pond, a lake the size of several football fields, filled with red liquid. Back to the process. The solution, now cleared of impurities, is cooled to 200 degrees Fahrenheit, and tiny alumina crystals are added as seed. Aluminum oxide starts to crystallize, settling as a white powder. This is pure alumina, with a chemical formula of aluminum 2O3. It looks like white flour and has nothing to do with the metallic aluminum we know. The alumina is washed, dried at 2000 degrees Fahrenheit, and you get a white crystalline powder that's 99.5% pure. Now it's ready for the toughest stage, electrolysis. And this is where the real show begins. I'm standing in an aluminum smelter in Iceland, one of the largest in the world. Why Iceland? You'll see in a second. In front of us stands an electrolysis hall nearly a mile long. Inside, hundreds of electrolytic cells, each the size of a small swimming pool. From here comes a roar like hundreds of airplanes taking off all at once. Look at one of these cells. It's a steel structure 20 feet long, 8 feet wide, and 3 feet deep. Inside, molten cryolite, a mineral that melts at 1800 degrees Fahrenheit. Alumina is added to this melt, and it dissolves in the cryolite like sugar in coffee. Massive graphite anodes, rods as thick as tree trunks, plunge into the bath from above. Below, the entire bath is lined with graphite blocks. That's the cathode. An electrical current of 150,000 amperes at 5 volts runs between the anode and cathode. That's 3/4 of a megawatt of power per bath. What happens under electricity's force? Aluminum oxide breaks down. Aluminum settles at the bottom of the bath as liquid metal, while oxygen bonds with the graphite anode, forming carbon dioxide. Pure aluminum's melting point is 1950 degrees Fahrenheit, but in molten cryolite it stays liquid at 1800 degrees. That's why the process is so energy intensive. You've got to maintain temperatures of almost 2000 degrees around the clock, plus push massive amounts of current through the molten bath. Producing 1 ton of aluminum takes about 15,000 kilowatt hours of electricity. That's how much the average American home uses in a year and a half. Now it makes sense why there's a plant in Iceland, right? They've got cheap geothermal and hydroelectric power. Aluminum smelters only get built where electricity is cheap. Iceland, Norway, Canada, the Middle East near natural gas fields, China near hydroelectric dams. Electricity costs make up about 40% of aluminum's total production cost. Each cell runs non-stop for 2 to 3 years. If you cut the power, the cryolite solidifies and you'd have to completely tear the cell apart. That's why these plants operate 24 hours a day, 365 days a year. Shutdowns only happen for major overhauls. Watch how metal gets tapped. Every 2 to 3 hours, a special vacuum ladle sucks liquid aluminum from the bottom of the cell. About a ton of metal comes out each time. The temperature of the liquid aluminum is 1800 degrees Fahrenheit. It glows bright orange and looks like molten silver. The liquid aluminum gets poured into 20-ton transport ladles and hauled to the casting facility. Here the metal gets cleaned of impurities. They blow chlorine or argon through it, which removes dissolved hydrogen. If hydrogen stays in, the metal will have pores and become brittle. Then the aluminum gets poured into mold. The most popular form is a 25-ton ingot about the size of a dining table and 2 feet thick. These ingots head to rolling mills where they get turned into sheets, foil, and profiles. They also cast cylindrical billets for extrusion, pushing through a die to create complex profiles. Here's an interesting detail. The graphite anodes gradually burn away during electrolysis. Oxygen released from the alumina bonds with the carbon in the anode, forming carbon dioxide. Each anode weighs about 500 pounds and burns out in 3 weeks. Then it's replaced with a new one. At a large plant, they swap out up to 50 anodes every single day. The anodes themselves are made from petroleum coke, a residue left over from oil refining. The coke gets mixed with pitch, pressed into molds, and baked at 2300 degrees Fahrenheit. What comes out is a graphite block with enough electrical conductivity for electrolysis. Anode production is a massive industry all on its own. Let's talk about the global numbers. Each year, humanity produces about 65 million tons of primary aluminum. That requires roughly 130 million tons of bauxite. It consumes around 950 billion kilowatt hours of electricity. That's 3% of all the electricity generated on the entire planet. China produces around 37 million tons of aluminum a year, nearly 60% of global output. Russia, about 4 million tons. Canada, 3 million. India, 4 million. The United Arab Emirates, 2.5 million. The US produces just 1 million tons, even though it consumes close to 5 million, importing the rest. The price of a ton of primary aluminum on the world market ranges from $2,000 to $3,000, depending on electricity prices and demand. For comparison, a ton of steel runs $600 to $800, a ton of copper around $9,000. Aluminum sits in the middle, not the cheapest, but more affordable than non-ferrous metals. The most interesting thing about aluminum? You can recycle it almost infinitely without losing quality. Remelting old aluminum takes only 5% of the energy compared to producing it from ore. That's why around 35% of all aluminum comes from scrap. Your aluminum soda can might have had a previous life as an airplane part or a window frame. Thanks for joining me on this journey from the jungle to the factory. If you enjoyed it, hit that like button and subscribe. Watch liquid steel pour from a ladle, glowing white at 3,000 degrees, bright enough to burn your retinas instantly. 20 tons cascading like luminous waterfall into molds, each splash throwing sparks 50 feet. This isn't new steel from ore, it's recycled. Yesterday's junked cars, demolished buildings, scrapped appliances melted and reborn. America recycles 80 million tons of steel annually, more than all other materials combined. That rebar in your building's foundation? Average age, 73 years through 4 previous lives. How does rusted scrap transform into structural steel stronger than original? Why does recycled steel outperform virgin steel in crucial applications? Stay with us. You'll witness industrial-scale alchemy turning garbage into skyscrapers and discover steel's shocking secret. It's infinitely recyclable without quality loss, forever. Nucor Steel's Berkeley facility in South Carolina processes 3 million tons annually, enough steel to build 15 Golden Gate bridges yearly. The scrapyard stretches half a mile, mountains of metal sorted by type. Shredded cars pile 6 stories high. Railroad rails stack like pickup sticks. Crushed appliances form metal glaciers. Giant cranes with electromagnets strong enough to lift entire automobiles move continuously, sorting, stacking, organizing chaos. Watch the shredder operation. A hammer mill the size of 2-story house contains rotating drum with 50 hammers, each weighing 300 pounds. Cars feed in whole, no disassembly required. In 8 seconds, automobile becomes fist-sized chunks. The noise defies description, continuous thunder as metal destroys metal. The shredder processes 100 cars hourly, 6,000 monthly. Every junked vehicle in America eventually passes through facilities like this. Nothing wastes. Even copper wiring gets separated and recycled independently. The electric arc furnace, EAF, is where steel is reborn. This vessel, 40 feet diameter and 30 feet deep, operates through electrical violence. 3 graphite electrodes, each 2 feet thick and 15 feet long, descend from the roof. When power flows, 90 megawatts, enough electricity for 70,000 homes, arcs jump between electrodes and scrap, generating temperatures exceeding 5,000 degrees. The initial charge contains 200 tons of scrap steel loaded via overhead buckets. Operators lower electrodes carefully. Too fast, they shatter. Too slow, productivity suffers. The arc strikes with deafening crack, visible through protective glass as blinding white plasma. Metal begins melting immediately. The sound evolves from cracking to roaring as molten pool forms. Watching through infrared cameras reveals the chaos. Solid metal liquefying, impurities rising as slag. The melt cycle takes 45 minutes start to finish. Chemistry happens through violence and precision simultaneously. Oxygen lances inject pure oxygen into molten steel at supersonic speeds. The oxygen burns impurities, carbon, sulfur, phosphorus, creating slag that floats atop the denser steel. Temperature reaches 5,800 degrees at plasma core, hot enough to vaporize iron itself. Cooling water circulates through furnace walls at 5,000 gallons per minute, preventing meltdown. Alloying additions fine-tune steel composition. Computer-controlled systems add precise amounts of manganese, chromium, nickel, elements determining final properties. High-strength rebar requires different chemistry than structural beams. The metallurgist's console displays real-time analysis via spectrometer. Laser vaporizes steel sample. Computer analyzes emitted light, identifying every element present to parts per million accuracy. Adjustments happen in real time. Chemistry perfected before tapping begins. Tapping releases the dragon. The furnace tilts hydraulically, massive vessel rotating on trunnions. Molten steel pours through tap hole into waiting ladle. Refractory-lined bucket containing 40 tons of liquid metal. The pour takes 6 minutes. Continuous stream of glowing steel creating updrafts so powerful, they lift dust and debris into the air. The temperature, 3,050 degrees, radiates heat felt 200 feet away. The ladle, mounted on railcar, travels to continuous caster. This machine revolutionized steelmaking, replacing individual mold casting with endless process. Molten steel flows from ladle into tundish, then into water-cooled copper molds oscillating up and down. As steel contacts mold, outer shell solidifies while interior remains molten. The strand, continuous ribbon of steel 8 inches square, emerges from bottom at controlled speed, bent gradually from vertical to horizontal through roller system. The hot rolling mill is where shape is born. The continuous cast billet, still glowing red at 2000 degrees, enters the roughing mill. Giant rollers, each weighing 30 tons, squeeze the steel, reducing thickness while increasing length. The transformation is violent. 8-inch square becomes flat bar 6 feet wide and 1/4 inch thick in 7 passes through successive roller stands. Watch the mill operation. The steel screams through at 40 miles per hour, extending like taffy as rollers compress it. Water jets cool rollers constantly. Without cooling, the steel would weld itself to roller surfaces. Scale. Iron oxide forming on surface gets blasted away by high-pressure water, creating permanent rainbow mist in the mill. The noise is beyond hearing protection. Low-frequency vibration felt in bones. One operator describes it. Steel doesn't want to be flat. We convince it otherwise through controlled violence. Cooling determines final properties through metallurgical magic. After final rolling pass, steel enters cooling bed, where water jets precisely control cooling rate. Fast cooling creates hard, brittle steel. Slow cooling produces soft, ductile steel. Controlled cooling, varying rates across thickness, creates exactly desired microstructure. Computer systems adjust water flow based on steel grade, thickness, ambient temperature. The coiler winds finished steel into massive coils, 40 inches wide, 1 mile long, weighing 25 tons. These coils ship to manufacturers producing everything from automobiles to appliances. Some steel goes to galvanizing lines where molten zinc coating prevents rust. Other steel gets further processed, cold rolled for precision applications, annealed for formability. But the core material, recycled steel, remains unchanged, ready for another century of service. Steel recycling accelerated during World War II when scrap drives collected every available piece of metal for weapons production. Post-war, technological advances made recycling economically viable. The electric arc furnace, developed in 1960s, eliminated need for iron ore. Recycling became primary production method. By 1980s, mini-mills using EAF technology revolutionized the industry, undercutting integrated mills using blast furnaces. Today, America produces 70% of steel from recycled scrap. Traditional integrated mills using iron ore and blast furnaces still exist but increasingly rely on scrap supplementation. The transition reflects economic and environmental reality. Recycling uses 60% less energy than primary production. A single steel mill prevents mining hundreds of thousands of tons of iron ore annually. The industry transformed from extraction to circulation, steel cycling endlessly through economy. Carbon emissions drop 65% using recycled steel versus virgin production. Industry saves $58 billion annually avoiding ore mining and processing. Each recycled ton prevents 4 tons of raw material extraction. Ore, coal, limestone combined. Here's the secret we promised. Steel is infinitely recyclable without degradation. Unlike plastic degrading with each recycle, steel maintains properties indefinitely. That nail holding your wall could have been Roman sword, railroad spike, Model T chassis, World War II tank, 1960s Cadillac, demolished skyscraper, and now construction steel. Same iron atom serving humanity for millennia. The crystal structure reforms perfectly during melting, erasing all history. Impurities burn away in the furnace, chemistry optimized through modern metallurgy. From junkyard to job site, the transformation completes. We've created closed-loop system where waste becomes resource, garbage becomes infrastructure. That bridge you drove across, those rails carrying freight, the frame supporting your office, all contain steel recycled dozens of times. The metal never tires, never weakens, never remembers its past. We've mastered material that improves through use, strengthened by human engineering beyond nature's intention. Steel isn't consumed. It circulates, eternally useful, permanently valuable, waiting only to be reshaped for next purpose. Civilization built on metal that refuses to die. Millions of tons of steel get forged worldwide every year, but only a handful become true mechanical titans. Picture a part weighing 30 tons. That's like 10 adult elephants compressed into a single ring. Here's the paradox. This behemoth must be machined to within a micron, thinner than a human hair. One of these bearings costs up to $3 million, and if it fails, the losses hit tens of millions. How do you make a steel monster perform with Swiss watch precision under thousands of tons of pressure? Stick around till the end, and I'll reveal the secret engineers keep hidden. What actually happens to metal when it gets shocked in oil? And why, without one critical step, this 30-ton beast will shatter like glass? You've never looked at metal this way before. I'm standing right now next to what will become a bearing for a tunnel boring machine shield. This is a steel ring 26 feet in diameter, weighing around 30 tons. And here's the most amazing part. This massive thing needs to be machined to within 0.02 of an inch. That's thinner than a human hair. Let's start from the very beginning, with material selection. For bearings like these, they choose special alloy steel or similar alloys. This steel contains chromium, molybdenum, and other alloying elements that make it super strong and wear resistant. Interesting fact, Chinese engineers developed an improved version of this steel specifically for 26-foot bearings, the largest in the world. The first stage of production is forging. Steel blanks are heated to 2,000 degrees Fahrenheit and forged under massive presses applying thousands of tons of force. The forging process aligns the metal's grain structure, making it stronger and more uniform. Here's a press as tall as a 3-story building that came down on red-hot steel with enough force to flatten a bus. After forging comes rough turning, enormous lathes, some the size of a 2-car garage, machine the blank, shaping it into a ring. The cutting tools for these lathes are made from tungsten carbide, a material 10 times harder than regular steel. Even so, these cutters wear out after just a few hours of work. Now for the crucial stage, heat treatment. This is what transforms ordinary steel into a nearly eternal material. The bearing ring is loaded into a giant furnace and heated to temperatures between 1550 and 1650 degrees Fahrenheit. At this temperature, the crystal structure stabilizes, ready for the next shock. Then comes quenching, the most dramatic moment in a bearing's life. The red-hot ring gets rapidly cooled by plunging it into an oil bath. The temp drops from 1600 to 300 degrees Fahrenheit in a matter of minutes. The oil hisses, boils, creating clouds of vapor. This sharp temperature shock transforms the steel's internal structure into martensite, a super hard crystalline form. But hardened steel has a problem. It's brittle as glass. One hit, and the multi-ton ring could crack. That's why the next step is tempering. The bearing gets heated again, but this time only to 350 to 500 degrees Fahrenheit. It's held at that temperature for 4 to 8 hours, then slowly cooled. Tempering reduces internal stress, makes the steel less brittle, but keeps the hardness. After heat treatment, the bearing has to go through rigorous inspection. They use ultrasonic equipment that can find an internal crack smaller than 8 inches. They also check microstructure samples. They take small pieces of metal and look at them under a microscope. You need 100% martensite with no retained austenite. Now begins the most precise stage, precision grinding. This is what separates a simple steel ring from a high-precision bearing. Look at this grinding machine. It's a specialized piece of equipment that costs several $1 million. The abrasive wheel spins at 5,000 revolutions per minute, removing microscopic layers of metal. Grinding happens in multiple stages. First comes rough grinding, which removes about 1/10 of an inch of material. Then finish grinding, which works to within 5 microns. Each pass of the grinding wheel is monitored by laser sensors that measure material thickness in real time. But that's not the end. After regular grinding comes super finishing, a process that makes the surface incredibly smooth. They use fine-grained abrasives and special techniques that reduce surface roughness to fractions of a micron. Under a microscope, this surface looks almost like a mirror. Why is this precision critical? Because these bearings operate under incredible loads. Take a tunnel boring machine, a beast that chews through solid rock. The cutting head, 57 feet in diameter, spins as it tears into granite. The force acting on the bearing reaches thousands of tons. If the bearing surfaces are uneven, even by a few thousandths of an inch, stress concentration zones appear. Metal at those points starts wearing down, heating up, and the bearing will fail. For large bearings, a segmented design is often necessary. A bearing over 30 feet in diameter can't be made in one piece. It simply won't fit in any heat treatment furnace. So they're made from separate segments, each machined individually, then all joined together with micron-level precision. The joints between segments must be so precise you can't even feel them with your finger. Interesting detail, for wind turbine bearings, they often grind a special profile called a crown. This isn't a decorative element. The crown distributes the load so maximum pressure falls on the center of the bearing, not the edge. If the load concentrates at the edges, premature wear occurs. The crown might be only a few thousand inches tall, but its shape is calculated by sophisticated computer programs. Let's talk about scale. One company, Rote Erde, manufactured over 2,500 bearings for tunnel boring machines in 3 years of operation. Each one unique, engineered for a specific machine and geological conditions. The cost of a single bearing ranges from $500,000 to $3 million depending on size. Sounds like a lot? Now picture this. If a bearing fails deep inside a tunnel, repairs can cost tens of millions and halt construction for months. The service life of these bearings is measured in decades. A wind turbine bearing must run for at least 25 years, generating millions of rotations. A bearing for a tunnel boring shield can chew through 15 miles of solid rock, spinning day and night for 3 to 4 years. Quality control here is absolute. Every bearing gets checked on a coordinate measuring machine, accurate to 200 thousandths of an inch. It's a room-sized machine operating in a temperature-controlled room, plus or minus half a degree Fahrenheit. Why such precision with temperature? Because steel expands when heated. A temperature swing of just 2 degrees can change the bearing's size by several thousandths of an inch, enough to ruin all measurements. They also run fatigue tests. They take metal samples from the very first batch and cyclically load them millions of times, simulating years of operation. If a sample fails before the calculated lifespan, the entire batch gets rejected. Harsh? Yes. But there's no other way. Billions of dollars in investments and human safety are on the line. The coolest thing about all this, the combination of gigantic size and incredible precision. It's like building a clockwork mechanism the size of a house. A part weighs a ton, but has to be accurate to within microns. A deviation you can't see with the naked eye can destroy the entire structure. And to keep my channel from falling apart, I'm counting on your comments and subscriptions. Subscribed? You sure you subscribed? And now? Alright then, let's continue. Engineers are constantly improving the technology. Right now they're testing new coatings for bearings, nanostructured films just a few microns thick that can double their lifespan. They're also developing sensors built right into the bearing that monitor temperature, vibration, and wear in real time. These smart bearings can warn you about a problem a month before it fails.